In my geometry classes, I usually study several triangle centers, especially the 4 classic triangle centers, which I'm going to talk about. And what's interesting is when we look at them and build them, I wind up finding these triangle centers and asking students what's special about these lines. And sometimes maybe the answer's too obvious, but sometimes students don't really see it as that special of a property that 3 lines intersect at a single point. But let me construct here. You can think about lots of different ways. If you have 3 lines, they could all be parallel. Let me use GeoGebra to create a bunch of parallel lines. They may not intersect at all, right? Or you could have 2 parallel lines and say a 3rd line that intersects across the 2 like that. Or you could have 3 lines that form a triangle. Let me blank this out and start over. Okay. So there's lots of ways that 3 lines can intersect and not intersect at one single point. When they do intersect at a single point, we call that concurrent. We say the 3 lines are concurrent. Let me build a picture here of 3 lines that are concurrent, in this case at the point B. So that's actually a pretty special property. If I take 3 random lines somehow generated, they're probably not going to intersect at a single point, right? It's a special property that they do actually intersect at single points. And for triangles, there's lots of ways we can define special lines, and in many, many cases, they actually do intersect at single points that we call centers of triangles. There's other ways to define centers, but one common way to come up with one is based off of special lines. Clark Kimberling has an encyclopedia of triangle centers on his webpage, which actually contains tens of thousands of triangle centers. But there's 4 really, really common ones, I call them the classic centers, known by the ancient Greeks back in the days of Euclid, that I'm going to show here. Let me get and turn the grid off. So let's say we have a triangle ABC. Let me turn off some of the labeling as well. We don't need to label everything. Let's do new points only. So I'm going to go over the 4 classic centers here. 2 of them are associated with circles, the incenter and the circumcenter, but let's do the ones that are not first. Let's look at the centroid first. So each side has a midpoint. I can use the midpoint tool to quickly find those with GeoGebra. And if we take a line from a vertex to the other side, we call that a Sevian, the one named after Siva, the ancient mathematician. If we go to the midpoint, it's called a median, and the 3 medians actually intersect at a single point, which is called the centroid. So that's one of the classic centers, the centroid. And so that is the centroid. Nice thing about GeoGebra, we can see that every triangle has a centroid, and the 3 medians will always intersect at a point. Let's see, let's delete the medians. Another one that's not associated with a special circle or anything, but is still called a center of a triangle, is the orthocenter. The orthocenter is the intersection of the altitudes. We call it an altitude because it helps us think about how tall a triangle is. Now the altitude may go outside of the triangle. Like in this case, if I think of side AC as the base, the altitude's inside the triangle. I can do the perpendicular line to the line containing that side. But if I have an obtuse angle there, then the altitude may actually go outside the triangle. The centroid's always inside the triangle. The orthocenter might not be. So I'm going to go ahead and, since I'm talking about the orthocenter, add the lines containing all of the sides. So from each vertex, we can make a perpendicular line to the other side, which we would call the altitude. And the 3 of those always intersect at what's called the orthocenter. So that point would be called the orthocenter. So for any triangle, whether it's obtuse, acute, scalene, equilateral, whatever, you're going to have an orthocenter. Sometimes it's inside the triangle, sometimes it's outside the triangle. Okay, the last 2 have to do with, of the 4 classic centers, have to do with circles as well. Let's do the circumcenter next, since that circle's easier to make. So the circumcenter is the center of a circle that goes through all of the vertices, is why they call it that. It's also the intersection of the perpendicular bisectors. So I have a tool for that in GeoGebra. I can just click on each side. There's a line that's perpendicular to the side and goes through the midpoint. If you do the three of those, they intersect at a single point called the circumcenter. And I can, once I define it, I can use my center, not center and radius, center through a point, go out to any vertex, and it's going to go through all three because that's the circumcircle. So there's the circumcenter, which is the intersection of the three angle or perpendicular bisectors. The angle bisectors are going to give us the incenter in a minute. And this one's the center of the circumcircle. The incenter is the center of the incircle, which we'll see. So let's do that one last. So the incenter itself is the intersection of the angle bisectors. It's the point that's equidistant from all three sides. So let's see, we have a tool for angle bisectors. So any point on that line is equidistant from sides AB and AC. Any point on that line is equidistant from the other two sides. So that point, the intersection is equidistant from all three sides, which means it also, if you click on the sides, it does the external angle bisector as well. Let me actually use the tool and do it. But you get the incenter. Okay. That's the center of a circle. If we go out perpendicular to the sides, that's going to be tangent to all three sides. This one's a little trickier to construct. I can't just draw it if I want to get it exact. I need to use the perpendicular line tool and go from the center perpendicular to one of the sides to find the shortest distance. And then I can use that to make the circle. So there's the incenter at D. I use the point E to find one of the in-touch points, the points of tangency with the sides. So every circle has an incenter inside, which is the center of the incircle, which is tangent to all three sides. So those are the four classic centers. There's an interesting property between three of those, known as the Euler line, that you might want to look into if you haven't heard of before. Three of them are collinear. One of them is not.